Yes, dear. Okay, I see the question. Does this mean that even if probability is low and information generated is high, still the entropy is low? It is only high when probability is 0.5. Can you elaborate? I'm not audible. Am I audible?
Yes, you are audible. Maybe the volume is low.
Okay, I don't know how to increase the volume from my side. Is this better?
Yes.
Okay, so the question was that if the probability is low and information generated is high, still the entropy is low. So that is exactly the point that I was trying to make. When you say the probability is low, we are talking about the probability of one of multiple possible outputs being low, right? If let's say you are considering a variable with 16 possibilities, it could be that probability of one of those 16 possibilities is very low. And whenever that possibility occurs, then indeed the information generated I of k is very large. But when probability of all the other 15 possibilities are large, then what happens is most of the time they only end up happening. And whenever they happen, because the probabilities are large, log base 2 of 1 over p of k is small, they don't end up generating too much information. And so on average, that source becomes not much informative. H of x becomes small. That is the analogy I gave, that in a container, if there are 16 molecules, if only one is vibrating a lot, meaning it has high information content, it doesn't mean that the overall container will be hot. The overall container will become hot only if all 16 of them are vibrating equally. That happens when P of k becomes 1 over 16 in this example. Does it help? Okay, good.
Yes, so we can continue with the session.
Okay, so I will now go to my next topic, which is the topic of noiseless channel coding. There is one part which I will cover, which is about the entropy at the receiver of a noisy channel. Okay, that is also a very interesting concept, but we will maybe get into that when we take the next topic, which is noisy channel coding. Right now, for the noiseless channel coding, the concept of entropy as we have defined is all that we need. So let us proceed with that. Okay. So this is the general diagram of a digital communication system that I had shown to you yesterday. And this topic of noiseless channel coding, also known as source encoding, is very much an integral part of today's communication technology. And that is what we are going to study today. Now, maybe one question that you might have had or may not have maybe chance to think that much about it, but if you recall that entropy curve for a binary source, Bernoulli source, had values which were fractions, right? The highest value was 1. Everything else was between 0 and 1. So how can bits be 0.5 bit or 0.25 bits or zero point 0.7 bits? So that is one possible question that you might have had. The answer is that if you toss a coin individually, obviously it can be either head or tail, 0 or 1. So at a time, it cannot be in fraction. But what if you don't look at it in isolated manner, but you consider a large sequence of such tosses, coin tosses, a large sequence of random experiments. Hello? No, I'm busy. I'll put it. Okay. Sorry for the interrupt. So the one realization that engineers had was that anytime we consider the engineering design of an informative system, a communication system, typically we are not just given one particular data bit to be stored or transmitted. Yes. But instead it is almost kind of a large sequence, never-ending sequence of information or bits that is given to us. So when we consider such large data sizes, then it kind of makes sense to say that entropy is 0.5 bit. What it means is that only half of the bits that are generated actually contain information. If the source generates 10 million bits, then it can be shortened to 5 million bits because h of x is 0.5. If h of x is 0.7, then 10 million can be shortened to 7 million bits. That too without losing any information. That is the definition, that is the practical significance of the definition of entropy, h of x. The h of x has just an intuitive or a conceptual aspect to it. We can kind of relate to it purely from an intuition point of view. But from an engineering design point of view, where this concept of entropy helps in a very concrete manner is that it tells us how much data compression is possible. And that is the topic that we will be looking at today. And this topic, which is the topic of data compression, also known as source coding or noiseless channel coding, obviously has large implication in today's world because, as we know, there is a large amount of data that gets generated over all this YouTube and Facebook and Instagram. And all of this data has to be stored. And if that storage requirement can be halved or can be even shortened by some extent, then it will provide obviously a very large benefit. So that is the problem that we're going to look at today. I'll skip over this slide because this relates to the noisy channel coding. We'll come back to it later on. Okay, so we will for this particular lecture, our problem is going to be the data compression problem or source coding problem or noisy channel coding problem. Is going to be that whenever we are given some large data set, let's say it's a binary data set which may have a lot of zeros and ones. We want to compress it. And that today is done effortlessly by WinZip or any other archival software. But what is the idea behind it? And by the way, WinZip is not the ultimate answer, right? There are a lot of researchers in academia, in the industry, everywhere, which are working on how to more efficiently compress all the data. A lot of these smart engineers and scientists are, as I said, hired by companies like Google and Facebook and so on and so forth. Because it directly, if you solve this problem more efficiently than how it is solved today, then you reduce storage requirement at these big companies, which immediately translates to a huge reduction in the cost. I understand that many of these companies are constantly looking at startups in the domain of the source coding. And anytime they find a potential startup with high potential, they go and buy it out. And then they own all the patents and everything. And then the owner of the startup becomes very rich also. So basically, the message that I want to give to you is that if you end up doing such development, then that would be a very quick path to becoming very, very rich in a very short time. So basically, the timeliness and the relevance of this problem cannot be overstated. The problem is basically what are the good algorithms that achieve the maximum data compression, and what is the maximum that we can achieve in some sense. Those are the problems that we will be looking at. We obviously won't be studying this problem in the level of engineering depth that some of these companies and the engineers and the scientists working at or working with these companies are looking at. We'll be looking at kind of an introduction to this problem. And although it means that we are going to simplify things a lot, the good thing is that the simplified model is still pretty powerful, and it will give us almost all the conceptual insights that are needed to fully appreciate the problem. Okay. So what is the simplification that we are going to do? We are going to restrict to only those type of informative sources. We are going to call them DMS, discrete memoryless sources, which, as the name suggests, are first of all discrete, right? They are not analog in nature. And secondly, they are memoryless, meaning that one symbol is independent of the previous symbol or the next symbol. So that is why it's called discrete memoryless source. Now look at these two different sources. A playwright composing some drama. Can you suggest some book on quantum computing? Where does this question come from in the context of what I'm talking about? I don't know who asked that question. Professor Mithrwal?
We can basically, we'll be taking this question when we start quantum information theory, which would be next week. This particular week, we are focusing more on fundamentals of physics and fundamentals of communication system theory. And the books for these two topics are already shared on Canvas. For quantum computing part, we'll be starting from next week. So probably the expert speakers there could suggest these books.
Yeah. Um, but I mean, I, what I don't know, because this is almost like a one-way transfer of information or one-way communication. I hope that I have not lost the attention of the participants. Um, there's this question about what is the quantum communication textbook. I don't know how it relates to anything that I have been talking about.
I mean, those linkages would be clear when we have next session, because the immediately after you there would be a session related to quantum communication, and we have basically the research scientists from IBM, so they are going to discuss about these. I mean, basically applying these classical theory in the quantum domain.
Uh, so Professor Mitra,
Yes.
maybe what I am sensing is that uh, the participants are kind of not sure what has this to anything to do with the main topic of quantum communication, right?
Yeah,
What-
I mean, most of them are interested in quantum communication, but then, of course, there are some. I mean, many of them who will be not having background in this particular information theory. I'm not saying all of them, but many of them may not be knowing these things. So these things are the basics which are required to understand more advanced topics which will be covered in quantum communication.
Yeah, I mean, I agree with Professor Mithrawal that quantum communication, quantum computation, quantum information theory, in order to appreciate them, you have to have a good understanding of the classical counterparts.
Right.
And that is what we are covering in these lectures. Okay, so maybe in the interest of time, I will continue. So I will ask you this question, that if you consider two informative sources, somebody who is writing a play on their laptop, so that is obviously discrete generation of information, because every time you write, you have to press a particular key on your keyboard, versus a monkey who is punching the keys on a typewriter or a keyboard placed in front of it. Which of these two sources is memoryless? What do you think? Both are discrete, but only one is memoryless. Yeah, it's clearly the monkey who is a memoryless source, because uh, presumably it won't have any idea of which key it pressed before and which key it's going to press next. So believe it or not, this theoretical treatment that we are going to look at is going to assume the second type of sources. And you might rightfully wonder that, well, the real world sources are more likely to be first type of sources. It turns out that the ideas that you will develop for DMS can be generalized to the first type of sources, which are memory full sources. But the mathematical ideas are more easily developed for type 2 sources, DMS type of sources. And so we are going to assume that the source is DMS. And then, although we won't do it here, but once we get the concept, it can be generalized to more realistic memory full sources. The source coding, or noiseless channel coding, is simply a mapping from the source alphabet to bits. Okay. There are two types of maps. One is called fixed length map. If you have, let's say, 4 symbols, x1, x2, this should have been x3, typing mistake, and x4. Then you give 2 bits to individual symbol, and then that becomes your fixed length mapping. And then there can be a variable length mapping where you give different binary sequences of different lengths to different symbols. Now, for fixed length coding, maybe it's not a problem, but for variable length coding, the decoding could be an issue if one particular code word happens to be a prefix of some other code word. And what we mean by that, we will look at it later on. Specifically, a variable length code is uniquely decodable if no code word is a prefix of another code. So if you look at this particular mapping where I have 7 symbols, I have mapped it to this type of variable length sequences. This is uniquely decodable. For the same, for actually a case where there are 4 symbols, I do variable length coding and I have this type of assignment, x1 to 1, x2 0, 0, 0, 1, and 1, 0. Then this is not uniquely decodable because suppose we get a sequence 0, 0, 1, 0, 0, 1. Should I decode it first 2 zeros as x2, then 1 as x1, then 0, 0 as x2, and then x1, or x2, 0, 0, then x1, which is 1, and then let's see, uh, no, 0, 0, which is x2, then 1, 0, which is x4, and then 0, 1, which is x3. So the same sequence 0, 0, 1, 0, 0, 1, I can denote it in 2 different ways, and I don't know which one is correct. So this is not uniquely decoded. And typically, the preference is to avoid any codes which are prefix free, to use only prefix free codes. Avoid any codes that violate this prefix free condition. Okay, now we will look at this particular example little more detail, and it will become hopefully more clearer as we move along. So don't worry about it if you didn't fully understand what I am trying to say here. But this question I am asking now is that at least you see that there could be some decodability problem if you do this variable length coding, which you will never have if you do fixed length coding, right? See, in terms of coding, you are just sending zeros and ones. You don't have luxury to insert commas, right? There is nothing like comma in a binary data. But when you don't have comma, the receiver has to figure out on its own where to insert comma to separate 2 different symbols. If it is fixed length coding, then the receiver knows that after every 2 bits, I insert a comma. So there is no decodability problem. When it's a variable length map, then the receiver can still do the insertion of comma correctly only if this prefix-free situation is present. The question is that why to even bother with variable length maps when fixed length codes don't have any such issue? Any thought on that? efficiency. Yes. No, not security. Fading ways, no. To increase the entropy. No, entropy is something that is inherent to a source. The mappings don't increase or decrease it. Problems are different. Okay. See, the thing is that when we are looking at some informative source with many different symbols, especially when those symbols have different probabilities, as we saw, letter E has much higher probability than letter Q, then using equal length code words is going to be inefficient. And therefore, variable length coding becomes useful or required. And so let us look at now this variable length versus fixed length in terms of a binary tree. So the example that I had with 7 symbols, so this is the prefix-free example of those 7 symbols mapped to different binary strings. You'll see that each of these red dots is an assigned code word. And if you go from any of the assigned code word to the root of the tree, in no case there will be another red dot in your path, which means that no code is a prefix of another code. Right? You will see that here very clearly. If I go from x5 to the root, do I cut across any other red circle? No. Same thing with x6 or x7. An assigned code word is never part of a subtree of another assigned code word. That is another way to look at it. If I assign x3 here, 0, 1. By the way, every time I go leftward from the root, it is 0, rightward means 1. x3 is 0, 1 because left, right. x1 is 0, 0, 0, 0, 0, 0. So once I assign a node to a particular symbol, then I reserve the entire subtree underneath that node. I don't assign any other code word to that subtree. Right? So that ensures that the assignment is going to be prefix free. In contrast, this confusing case that I was describing just a moment ago is clearly violating the prefix free condition, because look at x3 and x4. x3 is prefix of x4. Alternatively, I assigned x3 here, and then I used one of the nodes in the subtree under x3. So this is a problematic assignment. Now, there is a nice concept called Kraft's inequality that we will quickly look at in context of noiseless channel coding. And to understand that inequality, we will maybe make some definitions. So n of L is the number of bits in the code word which represents a source symbol x of L, and n max is the length of the longest code. Okay. So, and then a of L is 2 to the power n max minus nl. It is basically the number of leaf nodes belonging to the subtree under x of L. So what do we mean by that? N of L, let's say for the first one, it will be 3. Why? Because we have assigned a sequence 0, 0, 0. We assign 3 bits to this first symbol. So n of L for this first symbol, n of 1 is 3. N max is the length of the longest code word. The longest code word is this one, and this one, 4 bits. So N max is 4. The subtree under the individual code word, how many leaf nodes does it have? For this one, there are 2 leaf nodes, which is 2 to the power 4 minus 2 to the power 3, 2 to the power n max minus n of l. Here, the subtree has 4 leaf nodes. Why? 2 to the power 4 minus 2 to the power 2. Same way here. I think I made a mistake here. This A2 should have been 1 actually, because you count that particular node also. It should be 2 to the power 4 minus 4, 2 to the power 0. And so A2 should be 1. It's a silly mistake that I made. Same way A5, A6 is also equal to 1. And then A7 is obviously 2. Are you fine with this definition? Basically, A of L is just counting the number of leaf nodes belonging to a subtree occupied by a particular assignment. What are the number of leaf nodes corresponding to the first assignment? These 2. Okay, I saw the question. Can you explain the tree again? This tree is basically just a mapping tree. I'm using this type of variable length coding. I have, let's say, 7 symbols, and I just arbitrarily decided to assign this type of bit sequences to these 7 symbols. Okay. Why did I make this assignment? It's just an example. There is no logic to it. What are these 7 symbols? They can be anything. They can be the letters of some alphabet. They can be some different shades of a color. They can be different pitches of some sound. I don't know. There are some symbols. After we make the assignment, all that we are asking is how many leaf nodes does a particular assignment have? So X3 has how many leaf nodes in its own subtree? Obviously 4. X4, obviously 4. What about X2, X5, and X6? We'll count them individually as their own leaf node. So it will be obviously 1. And then X7 and X1 are going to be 2 each. So those number of leaf nodes are what we are going to call A of L. Okay. Now the argument is that when you sum up A of L for all these 7 symbols, only if it is prefix-free mapping, only if it is prefix-free, okay? If it is violating prefix-free condition, then all bets are off. Only if it is prefix-free requirement is met, then summation of A of L, L going from 1 to capital L, we are going to claim, we are going to argue that it can never exceed 2 to the power n max. At the most, it will be 2 to the power n max. Many times it will be less than 2 to the power n max. What is 2 to the power n max? Obviously 16, because n max is 4. 2 to the power n max is basically all the leaf nodes that are out there. And because it is prefix-free assignment, because this individual subtrees never overlap with each other, they are disjoint. That's why when we count those subtree leaf nodes and add them up, that summation can never exceed 2 to the power n max. Does it make sense? So that kind of leads us to Kraft's inequality, that a subtree under an assigned code word of length n of L bits has 2 to the power n max minus nl leaf nodes. Since the code is prefix free, different subtrees for different code words are disjoint. Because they are disjoint, when I add all these A of L values, that summation can never exceed the total number of leaf nodes, which is 2 to the power n max. So summation of A of L has to be greater than or less than equal. Summation of A of L has to be less than or equal to 2 to the power n max. A of L is given by this formulation. Summation of 2 to the power n max minus n of L has to be less than or equal to the power n max. I cancel out 2 to the power n max from both the sides of this inequality, and then the result is this. Does it make sense? I don't know. This proof is not terribly hard to understand, but maybe in the flow of this particular presentation, I don't know if you could keep up with what I said. If not, that's fine. You can just search on Kraft's inequality and you will find very nice explanation describing its validity and its proof. So what does it tell us, Kraft's inequality? Kraft's inequality tells us that when you do this prefix-free assignment variable length coding, you look at what are the lengths of individual code words and put those lengths here and then sum them up, you will get some value which at the most will be equal to 1. The reason why this is interesting is because suppose somehow you did some mapping where the inequality become equality. So 2 to the power n minus nl summed up become equal to 1. In which other setting does this happen? What is another type of set of numbers, L of them, capital L of them, which when you add them up, that sum also becomes 1. In fact, we did this in the previous hour. You know, I'm saying, can you think of another mathematical concept where you're given a set of numbers which has this property that if you add all of those numbers up, you get 1. What is that set of numbers called? Sum of probabilities, correct. Actually, we called it probability mass function, right? whenever we are given PMF, basically the probability of L such symbols, when we add those probabilities, we are going to get 1. So if you make a leap of faith and say that this individual values 2 to the power minus NL is somehow some type of probability, it may not be the actual probability, but some probability, it's a pseudo probability, a probability that we make up. And that's why I'm not calling it P of L, I'll call it P hat of L symbol. And P hat of L is 2 to the power minus N of L. Alternatively, N of L is negative log base 2 of P hat of L. But if you look at this, negative base log base 2 of P hat of L, then that is the information content of a symbol with the probability P hat of L. That is how we define I of L, if you recall in just the previous lecture. But here this is N of L, number of bits that we are assigning to L symbol. When the Kratz inequality turns into the equality, then the code words become having length which is equal to the Shannon's definition of the information generated by the symbols having pseudo probability P hat of L. That is quite an interesting connection between the information definition versus some assignments that we are doing in a prefix-free manner. Okay, the rate of a source code is the expected number of bits required to represent a particular symbol. So if I have capital L symbols, then the rate, the average value of bits that I need will be equal to P of k times N of k. Why? Because N of k is the number of bits that I need for representing kth symbol, and P of k is the probability of kth symbol. So this is the standard definition of the expected value. For fixed length code, when we give same number of bits to all the symbols, and if there are total of capital L symbols, then R cannot be less than log base 2 of capital L, which makes sense. If I have 16 symbols, then on average I will need 4 bits per symbol. If I have 25 symbols, then I will need more like 5 bits per symbol, something like that. And the goal of source encoding is to find uniquely decodable code that minimizes the average value of R. Because if you can reduce R, then we are effectively representing the output of the source in a more concise manner. We are becoming more efficient in representing the information that is generated. And that is where the reason why we need to use variable length coding, this is a question that I asked you some time ago, becomes clear that we should be assigning short code words to the most likely symbols and large code words to least likely symbols. So think about it. This is this kind of strategy that we are doing. But here, this small nk is the length of the code word, but it also kind of represents the information that is being generated by that code word symbol. So in a way, what we are saying is that if we knew the information content of a particular symbol, then we should assign to it a code word whose length is equal to that information content. A fundamental theorem of information theory says that for a uniquely decodable source code, R can never be less than entropy of X. This rate R that we defined here can be made small, as small as you would like it to be, but not less than h of x. The best you can do is make n of k to be negative log base 2 of p of k. That will serve this purpose, this strategy. As soon as you do that, R becomes actually same as h of x. You can't do anything better than that. That is the source coding theorem or noiseless channel coding theorem. How to prove this theorem? That's kind of a very interesting topic. I don't know we have time for that. Maybe we won't be able to spend too much time on the proof of source coding theorem as of now. Maybe we'll take it up in one of the subsequent lectures. But the proof of this source coding theorem actually relates to that binomial random variable that we have defined in the previous lecture. And in proving that, we kind of start with that bicycle factory problem. Remember, I talked about it briefly in yesterday's lecture. We start from some such simple probability theory question, and then we think about it in detail, and then suddenly we realize that R can never be less than h of x. That is the kind of elegance of this mathematical line of thought. If I get a chance, I'll maybe quickly walk you through that proof tomorrow or day after tomorrow. But for the remaining maybe 5 minutes that I have, let me just go over two practical source coding algorithms which you may have or may not have come across earlier. The first one, Huffman coding, is pretty general algorithm that is likely to it's likely that you have studied it earlier. Lempelsive coding is a little more specific technique. Huffman coding requires the knowledge of PMF, probability mass function. Lempelsive coding is called one of those blind schemes. It doesn't require the probability knowledge. By the way, who has studied in any one of these two techniques before? Or both of these are new to you? Okay, so at least I don't see too many yeses flashing, so maybe it's not that most of you know about it. Okay, so this is just two schemes out of many different other schemes that belong to this source coding topic. They're called Shannon-Fano coding, Shannon-Fano alias, arithmetic, run length coding, etc. And as I said, this is a major area of current development. There are many proprietary algorithms and many advanced designs that are being developed, which are not being revealed in the journal papers, conference articles, textbooks, etc., which try to do the same thing. Okay, so this is a very fruitful area of research. But these two classical methods is something that are widely known, and we can also study it very nicely, quickly in our next 5 to 10 minutes. The Hoffman coding, what it does is it first of all looks at the probability of different symbols and arranges them in descending order. And then it runs an iterative algorithm. Okay, what does the iterative algorithm do? It's very simple. It takes the two lowest probability symbols and combines them into a new pseudo symbol. And then it goes back to step 1 and iterates the step 1 and step 2 again. It keeps on doing that. That's it. And then it keeps track of what it has done. Once it completes the iterations, by the way, when would the iteration stop? Because every time you combine two lowest probability symbols into one symbol, one virtual symbol, you reduce the number of total symbols by 1, right? Suppose you start with 6 symbols, and at the end of first iteration, you will have 5, then 4, then 3, 2, 1. Once you are down to one symbol, then you are at the step 3. At that time, you just work your way backward and then develop the entire mapping table. Let's take a look at how it happens. This is 6 symbols that we are given. These are the corresponding probabilities. They're already ordered in the descending order. What is the first thing it will do? X5 and X6, it will combine into a pseudo symbol or a virtual symbol. That virtual symbol in the second iteration came up here, star. Now star is still one of the two lowermost symbols. So it again will get combined into another virtual symbols. We keep on tracking the probability of the virtual symbols, which is sum of the two probabilities, the sum of the probabilities of two symbols that got combined. And so this process gets iterated. At the third iteration, now x2 and x3 ended up having the smallest probability. So they got combined, whereas this original tree remained intact. Now, in the fourth step, the two lowest symbols are both the virtual symbols that were formed in step 2 and step 3. So you combine them, and then you get this tree. The only thing that now remains is x1. And so you combine it to finally form the final virtual symbol whose probability has to equal 1, because now we have combined all of the symbols. Because you keep track of how you were combining symbols every time, basically you form this prefix-free binary tree, basically. Obviously, wherever there is a star, you don't need to worry about it. Only when you come across any one of these X's, you look at what the symbol binary assignments are. That is all there is to it. The Huffman coding would assign this variable length mapping to these 6 symbols. Look at what it did. It assigned a code word of this least length, this length of 1 bit, the most highest probability symbol x1. And the two smallest probability symbols x5 and x6, they were assigned the largest code words of length 4 bits. Now you can plug in those lengths you already know the probabilities. You can evaluate the product P of k times L of k, sum them up, and you get the value of capital R, the average number of bits per symbol that we have defined earlier. For this case, it becomes 2.2 bits per symbol. There are 6 symbols, so you can never get the number of bits to be less than 2. If it was fixed length, you would need 3 bits per symbols because it's more than 4. So you will need to assign 3 bits. Because it is variable length, you can now get to some value which is less than 3 bits. Here it is 2.2 bits. You can also calculate the entropy, which I have done here in the last 2 columns, and it turns out to be 2.18 bits. This again is the confirmation of the fundamental theorem of information theory, noiseless source coding, that R is not becoming smaller than h of x. Comes pretty close actually, but it's higher than h of x. Hello? Can I call you back? Okay, maybe I'll skip over this Lempelze coding because I have run out of time. It's not very relevant, I think, for the rest of the topics that we are going to discuss. But if you are interested in understanding Lempelze coding, I think there are excellent tutorials available on the internet. Even some textbooks are also very good in describing Lempelze coding, so you can study it on your own. Lempelze coding is actually a very famous scheme, and today whenever you use, I think, any one of the video or image representation algorithms, basically your digital camera and video camera, it's quite likely that it ends up using some form of Lempelze scheme, right? So it's a very powerful algorithm. Okay, so with that, I'll stop for today. And if there are any questions, please feel free to ask.
All right. Thank you, Professor Yasho Sabra. There will be, I think there is one question posted just now. So probably we can answer. If you have time, we can answer. You can answer that and then we'll stop.
What will happen when R is less than entropy h of x? So basically, if you try to make R to be less than h of x, then you're going to lose the information. So what do I mean by that? So suppose you have an informative source with, let's say, 8 symbols. So capital L is 8. And let us say that all these 8 symbols are equally likely. So their probabilities are 1 over 8. If you plug these probabilities into the formula for entropy h of x, you will see that the entropy becomes 3 bits. Negative p of k, log base 2 of p of k. Summation over L going from 1 to 8. When p of k is 1 over 8, then the entropy becomes exactly equal to 3 bits. What does it mean? According to this fundamental source coding theorem, you need R to be at least 3 bits to represent the occurrence of 1 out of these 8 symbols. That makes complete intuitive sense, right? Because you have 8 symbols. You cannot represent those 8 symbols using any less than 3 bits. Because they are all equiprobable, you can use fixed length coding. 0, 0, 0, 0, 0, 1, all the way to 1, 1, 1. And then you are done. And that mapping is going to be optimal. It is going to give you R, which is equal to H of X. Now, suppose that you say that, no, I want to be more ambitious. I want to reduce R to be some value less than H of X. In an extreme case, suppose you say that instead of 3 bits, I want to make it 2 bits. But with 2 bits, you can only represent 4 symbols at the most. You actually have 8 symbols, but with 2 bits, you can name only 4 out of 8. So what happens when you have occurrence of a symbol which you have not named? The actual source has 8 symbols. With 2 bits, you have kind of tied your hands and you have said that I am going to represent only 4 out of these 8 symbols because I want to make R equal to 2. The other 4 symbols, I'm not going to label them at all. I'm not going to assign any binary string to them. Because if I do, then my R cannot be less than 3. But the source doesn't know that. Source will keep on generating one of those 8 symbols. So whenever it generates a symbol which you have not assigned any binary string, then you are in trouble. You can't convey that information. You can't store it. You can't transmit it. So that would be a problem.
There is a follow-up question.
Yeah, I see that. H of X is the theoretical lower bound for R, so that there is no information loss. Correct. Correct. So as long as you make R to be equal to or greater than H of X, then according to this mathematical theorem, you're going to be able to reproduce the same exact information that was generated. And that actually came as a surprise to the engineers of those days, because in those days, people would assume that if suppose some data source generates a million bit of information, then you need a million bit of storage, or you need a million bit to transmit that amount of information. But here, this theorem says that, well, those million bits could be generated by the source, but if the entropy of source is only 0.1 bit, then you don't need million bit for storage. You need only 0.1 times a million, which is 1 lakh, 10 to the power 5, 1 lakh bits to be stored. And not only that, you reduce the storage requirement by 90%, but you don't lose anything. By storing or by transmitting only 1/10 the bits, you are still going to be able to convey the same amount of information that those million bits conveyed.
There is one more question. If you have probably, or otherwise we can take it tomorrow also.
Yeah, mixed state and data loss with entropy. I don't understand this question actually. Can you elaborate? Yeah, what do you mean by mixed state? How is noise connected to entropy? So right now we are focusing on noiseless channel coding. We have not brought in noise yet. The effect of noise we are going to consider in the lecture tomorrow.
Okay, so I mean, mixed state is something. Mixed state is something related to quantum mechanical. Somebody has posted, some participants. So basically, as I've told you earlier, this is more related to classical communication theory rather than quantum communication. Quantum communication will start from the next week onwards. All right, thank you. Thank you, Professor Vasala. We'll conclude this session here,
Okay.
and we'll continue with the same communication theory in next sessions tomorrow.
Okay. Sure.
Thank you. Bye.